November 25, 1940. Hatfield Aerodrome, England. Test pilot Geoffrey de Havilland Jr. advanced the throttles of prototype E0234 and felt the aircraft accelerate down the runway with surprising smoothness. Behind him in the second seat, engine installation designer John Walker watched the instruments as two Rolls-Royce Merlin engines powered what looked like an impossible aircraft into the sky. The de Havilland Mosquito was flying for the first time, and its revolutionary wing design was about to prove that one engineer's supposedly impossible vision could outrun anything the enemy could build. 30 minutes later, the yellow prototype touched down after a flawless maiden flight. What had just occurred would change aerial warfare forever. The wings that lifted the Mosquito were unlike anything ever constructed for military aircraft. They were built entirely from wood using techniques that aviation experts had declared structurally impossible. Yet these wings would soon carry aircraft to speeds exceeding 400 miles per hour, making the Mosquito the fastest operational aircraft in the world and earning it the nickname that would define its legend, the Wooden Wonder. This is the story of William Tamblyn, the senior design engineer whose wing construction methods violated every principle of conventional aircraft design and created a structure so revolutionary that it remained classified long after the war ended. His wooden wings used 30,000 brass screws, 2 layers of birch plywood, and adhesive techniques borrowed from furniture makers to achieve strength-to-weight ratios that exceeded aluminum construction. The wings that experts said would never work became the foundation for the most versatile combat aircraft of World War II. When William Tamblyn joined the de Havilland design team in 1936, military aviation was experiencing a fundamental transformation. Metal aircraft construction had become the global standard, relegating wood to training planes and obsolete designs. Aluminum offered advantages in strength, durability, and manufacturing efficiency that seemed to make wooden aircraft construction a relic of aviation's primitive past. Every major air force was investing heavily in all-metal fighters and bombers that represented the future of military aircraft. Tamblyn possessed an unusual background for an aircraft designer. His engineering training included extensive study of wooden construction techniques used in shipbuilding and furniture manufacturing. While his colleagues focused on metal fabrication methods, Tamblyn understood the structural properties of laminated wood construction that could achieve strength characteristics comparable to aluminum, while offering significant weight advantages. His knowledge of adhesive chemistry and joinery techniques would prove crucial when de Havilland began developing its most ambitious aircraft project. The concept that would become the Mosquito emerged from discussions between company founder Geoffrey de Havilland and chief designer Ronald Bishop in 1938. European tensions were escalating rapidly, and the Royal Air Force urgently needed new bomber aircraft capable of penetrating German air defenses. Conventional wisdom favored heavily armed bombers with multiple gun turrets and large crews, but de Havilland proposed a radically different approach based on speed rather than defensive firepower. The revolutionary concept called for an unarmed bomber fast enough to outrun enemy fighters. Such an aircraft would require exceptional performance that could only be achieved through dramatic weight reduction and aerodynamic efficiency. Metal construction techniques could not provide the smooth surfaces and precise tolerances necessary for the required performance levels. De Havilland concluded that wooden construction offered the only viable path to creating an aircraft with the characteristics needed for their revolutionary bomber concept. Air Ministry officials rejected the wooden bomber proposal immediately. The concept violated established doctrine that prioritized defensive armament over speed. Additionally, wooden aircraft construction was considered obsolete and unreliable for modern military applications. The ministry preferred proven metal construction techniques and demanded that de Havilland focus on conventional bomber designs using established engineering practices. The rejection seemed to end the revolutionary bomber concept before detailed design work could begin. Geoffrey de Havilland refused to abandon his vision and authorized continued development using company funds. The design team relocated to Salisbury Hall, a 17th-century manor house near the main factory, where they could work on the secret project without government interference. Chief designer Ronald Bishop assembled a small team of specialists, including Richard Clarkson for aerodynamics, Charles Wilkins for fuselage design, and William Tamblyn as the wing specialist responsible for developing the structural techniques that would make the impossible aircraft possible. Tamblyn faced unprecedented engineering challenges in designing wings for the high-speed wooden bomber. The aircraft needed to achieve speeds approaching 400 miles per hour while carrying significant fuel and weapons loads. Traditional wooden wing construction used internal frameworks of ribs and spars covered with fabric or thin plywood skins. Such methods could not provide the structural strength required for high-speed flight, while maintaining the smooth aerodynamic surfaces necessary for maximum performance. The breakthrough came from studying laminated construction techniques used in advanced sailing yachts and racing boats. Tamblyn realized that multiple layers of thin wood veneers bonded with modern adhesives could create composite structures stronger than conventional wooden frameworks while providing perfectly smooth external surfaces. The technique required precise manufacturing methods and exotic materials that had never been used in aircraft production, but offered the potential for revolutionary performance improvements. Tamblyn's wing design used a sophisticated sandwich construction method that became the foundation for modern composite aircraft structures. The wing framework consisted of two main box spars built from laminated plywood sections reinforced with spruce stringers. Between the spars, a series of precisely shaped plywood ribs provided the wing's aerodynamic profile while creating mounting points for fuel tanks, control surfaces, and equipment installations. The entire structure was covered with birch plywood skins, bonded to the framework using casein adhesive, and reinforced with nearly 30,000 brass screws. The construction process required manufacturing precision that exceeded normal aircraft production standards. Each wing was built as a single piece stretching from wingtip to wingtip, with no structural joints where the wing passed through the fuselage. This one-piece construction eliminated potential failure points while providing maximum structural strength, but required specialized tooling and assembly techniques that had never been attempted in aircraft manufacturing. The smooth plywood surfaces were covered with cotton fabric and treated with multiple coats of specialized dope to achieve mirror-like finishes. Advanced cooling system integration became another revolutionary aspect of Tamblyn's wing design. Instead of mounting engine radiators externally where they would create drag, the cooling systems were embedded within the wing structure itself. Carefully designed air passages channeled cooling air through radiator cores mounted inside the wing, with inlet openings in the leading edges and exhaust ports beneath the wing surfaces. This arrangement eliminated the external radiator installations used on contemporary fighters and provided additional forward thrust through the thermodynamic effect of heated air expansion. The manufacturing process required skills and materials that existed primarily in Britain's furniture and cabinet-making industries. Tamblyn worked with craftsmen from piano factories, yacht builders, and luxury automobile coachworks to develop production techniques capable of achieving the required precision and quality standards. Specialized adhesives were formulated to provide consistent bonding under the temperature and humidity variations encountered during flight operations. Quality control procedures exceeded those used for metal aircraft construction to ensure structural integrity throughout the operational lifetime. Wind tunnel testing revealed that Tamblyn's wing design achieved aerodynamic efficiency levels that exceeded all contemporary aircraft. The smooth wooden surfaces eliminated the drag penalties associated with riveted metal construction, while the precise contours provided optimal airflow characteristics throughout the flight envelope. Structural testing demonstrated that the wooden wings could withstand load factors exceeding those required for metal aircraft construction, while weighing significantly less than equivalent aluminum structures. The first complete wing assembly was mounted on the prototype airframe in October 1940, Ground testing revealed that the innovative structure exhibited none of the vibration or flexibility problems that critics had predicted for wooden construction. The wings remained perfectly rigid under maximum engine power, while demonstrating excellent response characteristics to control inputs. Static loading tests confirmed that the structure could withstand forces far exceeding normal operational requirements without exhibiting signs of structural distress or permanent deformation. Jeffrey de Havilland Jr.'s first flight on November 25 proved that Tamblin's wing design worked exactly as calculated. The prototype achieved level flight speeds exceeding 300 miles per hour during initial testing, demonstrating performance that exceeded most contemporary fighter aircraft, despite being significantly larger and heavier. Control response was exceptional, with the large wing area providing excellent maneuverability characteristics that would prove crucial during combat operations. Most importantly, the wooden construction showed no signs of structural problems during the demanding flight test program. Royal Air Force evaluation flights confirmed the revolutionary performance capabilities made possible by Tamblin's wing design. Service pilots reported that the Mosquito could outrun Spitfire fighters in level flight, while carrying bomb loads equal to much larger conventional bombers. The combination of speed, maneuverability, and load-carrying capacity exceeded anything previously achieved in military aviation. Air Ministry officials who had initially rejected the wooden bomber concept began requesting immediate production orders as German air defenses proved increasingly effective against conventional bomber types. Production planning required developing entirely new manufacturing processes to build Tamblin's complex wing structures in quantity. Traditional aircraft factories lacked the skilled woodworkers and specialized equipment necessary for laminated construction techniques. De Havilland established partnerships with furniture manufacturers throughout England, converting piano factories and cabinet-making shops into aircraft production facilities. The distributed manufacturing approach allowed rapid production expansion, while utilizing craftsmen whose skills were perfectly suited to precision wooden construction methods. The wing manufacturing process began with carefully selected timber imported from around the world. Canadian birch provided the primary structural plywood, while Douglas fir from the Pacific Northwest supplied the stringers and reinforcing members. Ecuadorian balsa wood filled sandwich panels where minimum weight was critical. Each piece of wood was inspected, graded, and seasoned according to specifications that exceeded those used for musical instrument construction. The quality control standards ensured consistent structural properties throughout the production process. Assembly took place in purpose-built concrete molds that provided the precise three-dimensional shapes required for Tamblin's wing design. The molds were manufactured to tolerances measured in thousandths of an inch, ensuring that every wing matched the exact aerodynamic profile developed during wind tunnel testing. Layers of plywood were positioned in the molds and bonded with adhesive applied under carefully controlled temperature and pressure conditions. The 30,000 brass screws were installed according to precise patterns that distributed structural loads throughout the wing framework. Combat operations proved that Tamblin's wing design provided performance advantages that fundamentally changed aerial warfare tactics. Mosquito bombers could penetrate German air defenses at speeds that made interception nearly impossible, allowing precision attacks against targets that were heavily defended against conventional bombers. The wooden construction proved remarkably resistant to battle damage, with the laminated structure able to absorb significant punishment while maintaining structural integrity. Repair procedures developed for field maintenance allowed battle-damaged aircraft to return to operations much more quickly than metal aircraft with equivalent damage. The success of the bomber version led to development of fighter and reconnaissance variants that fully exploited the performance potential of Tamblin's wing design. Fighter-bomber versions carried combinations of cannons, machine guns, bombs, and rockets, while maintaining speed advantages over specialized single-seat fighters. Photo reconnaissance variants achieved operational altitudes and speeds that made them virtually immune to interception, providing intelligence capabilities that influenced strategic planning throughout the war. Night fighter versions used the stable gun platform characteristics of the large wing to mount radar systems and heavy armament that dominated nocturnal air operations. Advanced variants pushed the capabilities of wooden construction to their ultimate limits. High-altitude interceptor versions featured extended wingtips that increased span to 59 feet, while maintaining the structural integrity necessary for combat maneuvering. The wing modifications were accomplished using the same laminated construction techniques developed by Tamblyn, demonstrating the flexibility and adaptability of wooden construction methods. Performance improvements included operational ceilings exceeding 40,000 feet and maximum speeds approaching 450 miles per hour. Specialized attack versions demonstrated the load-carrying capabilities made possible by Tamblyn's structural design. Anti-shipping variants carried 57mm cannons that could penetrate naval armor, while maintaining the speed necessary to attack heavily defended targets and escape before defensive fire could achieve effective range. Torpedo bomber versions featured wing modifications that allowed carrier operations, extending the versatility of the basic design to naval aviation applications. The adaptability of wooden construction techniques allowed rapid development of specialized variants that would have required extensive redesign using metal construction methods. German efforts to counter the Mosquito threat revealed the revolutionary nature of Tamblyn's wing design. Luftwaffe technical intelligence reports expressed bewilderment at British ability to achieve such exceptional performance using apparently obsolete wooden construction. German attempts to develop similar aircraft using metal construction failed to achieve comparable performance characteristics, demonstrating the unique advantages provided by advanced wooden construction techniques. The structural efficiency of laminated wooden construction remained unmatched throughout the war despite intensive development efforts by German and American aircraft manufacturers. Post-war analysis revealed the full extent of the technological breakthrough achieved by Tamblyn's wing design. Wind tunnel studies demonstrated that the wooden Mosquito wings achieved aerodynamic efficiency levels that were not equaled by metal aircraft until the introduction of jet-powered designs. The strength-to-weight ratios achieved through laminated construction exceeded those of contemporary aluminum aircraft, while providing superior damage resistance and repair characteristics. The manufacturing techniques developed for Mosquito production influenced post-war development of composite construction methods that became standard in modern aircraft design. The tropical climate failures that affected some Mosquito aircraft in the Far East highlighted both the strengths and limitations of wooden construction. Investigation revealed that structural problems resulted from poor quality control during wartime production, rather than fundamental design flaws in Tamblyn's wing structure. Aircraft built according to original specifications performed normally in all climate conditions, while those with construction defects experienced adhesive failures that led to skin separation. The investigation led to improved manufacturing procedures and alternative adhesives that eliminated the tropical climate problems. Scientific analysis of surviving Mosquito wings revealed the sophistication of Tamblyn's structural design. X-ray examination showed that the internal structure achieved load distribution characteristics that matched or exceeded modern finite element analysis predictions. The arrangement of plywood layers, reinforcing stringers, and attachment points demonstrated intuitive understanding of stress patterns that was not formally quantified until decades later. Tamblyn's empirical design methods achieved results that modern computer analysis confirms were mathematically optimal for the performance requirements. The legacy of Tamblyn's wing design extended far beyond the Mosquito program to influence fundamental developments in aircraft construction. The laminated construction techniques became the foundation for modern composite aircraft structures, used in everything from sailplanes to space vehicles. Adhesive bonding methods developed for Mosquito production evolved into the chemical bonding techniques that revolutionized manufacturing across multiple industries. The integration of structural and aerodynamic requirements pioneered by Tamblyn became standard practice in modern aircraft design. Manufacturing innovations developed for Mosquito wing production transformed British woodworking industries, and influenced post-war furniture and construction methods. The precision molding techniques developed for aircraft production found applications in boat building, automotive manufacturing, and architectural construction. Quality control procedures established for aircraft production raised standards throughout British manufacturing and contributed to post-war industrial competitiveness. The skilled craftsmen trained for Mosquito production provided the foundation for advanced manufacturing industries that emerged during the post-war economic expansion. Modern aircraft manufacturers continue to study Tamblin's wing design for insights into composite construction methods and structural optimization. Computer analysis reveals that the load paths and stress distributions achieved through empirical design methods were remarkably sophisticated despite the absence of modern analytical tools. The manufacturing processes developed for wooden construction provided precedents for automated composite manufacturing that became standard in contemporary aircraft production. Design principles established by Tamblin remain relevant for modern engineers developing advanced composite structures. Educational institutions use the Mosquito wing as a case study in innovative engineering that challenges conventional assumptions and achieves breakthrough performance through creative application of available materials and techniques. Engineering schools analyze Tamblin's design methods to understand how intuitive understanding of structural behavior can achieve results that exceed formal analytical predictions. The success of wooden construction in achieving metal aircraft performance demonstrates the importance of considering non-conventional solutions when conventional approaches prove inadequate. Restoration projects worldwide continue to demonstrate the durability and serviceability of Tamblin's wing design 70 years after the original construction. Surviving aircraft retain structural integrity that allows return to flight status using original construction techniques and materials. The ease of repair and modification that characterized operational service continues to benefit restoration efforts, allowing aircraft to be returned to airworthy condition using traditional woodworking skills. Modern restorations validate the long-term durability of laminated wooden construction while preserving the craftsmanship techniques that made the Mosquito possible. Museum displays and technical exhibits educate new generations about the engineering innovation that challenged established doctrine and achieved revolutionary performance through creative application of traditional materials. Cutaway wing sections reveal the sophisticated internal structure that provided exceptional strength while maintaining minimum weight. Interactive displays demonstrate the manufacturing processes that transformed furniture-making skills into aircraft production capabilities. The educational value of the Mosquito story continues to inspire engineers and designers facing similar challenges in applying innovative solutions to demanding requirements. Contemporary aerospace programs incorporate lessons learned from Tamblin's wing design in developing advanced composite structures for modern aircraft and spacecraft. The integration of multiple functions within single structural elements pioneered by the Mosquito influences modern design approaches that seek maximum efficiency through multifunctional structures. Manufacturing techniques that combine traditional craftsmanship with modern technology trace their origins to the production methods developed for wooden aircraft construction during World War II. William Tamblin received recognition for his contributions to aircraft design through appointment as Officer of the Order of the British Empire in the post-war honors list. His wing design innovations influenced his subsequent career in developing composite construction techniques for civilian aircraft and marine applications. Tamblin continued working with advanced materials and manufacturing processes throughout the jet age, applying lessons learned from Mosquito development to new challenges in aerospace engineering. His empirical approach to structural design provided a model for engineers working at the frontiers of materials science and manufacturing technology. The engineering principles established by Tamblin's wing design continue influencing modern aircraft development as manufacturers seek improved performance through advanced materials and construction techniques. The integration of structural, aerodynamic, and systems requirements pioneered by the Mosquito remains a fundamental approach in contemporary aircraft design. Manufacturing methods that achieve precise dimensional control and superior surface finishes through innovative construction techniques trace their origins to the production innovations developed for wooden aircraft construction. The Mosquito's operational success validated Tamblin's conviction that innovative engineering could overcome apparent material limitations and achieve performance that exceeded conventional expectations. His wing design proved that creative application of available materials and manufacturing techniques could produce results superior to seemingly more advanced approaches. The lesson remains relevant for contemporary engineers facing resource constraints and challenging performance requirements in developing advanced aerospace systems. On November 25, 1940, when Geoffrey de Havilland Jr. lifted the yellow prototype into the English sky, William Tamblin's impossible wing design began proving that innovation could triumph over convention. The wings that aviation experts had declared structurally unsound carried the Mosquito to speeds that made it untouchable throughout the war. 30,000 brass screws, birch plywood skins, and casein adhesive had created the fastest operational aircraft in the world, using materials that furniture makers understood better than aircraft engineers. The impossible wings that emerged from Tamblin's design office at Salisbury Hall revolutionized military aviation and established principles that continue influencing aircraft design 8 decades later. His wooden wings proved that exceptional performance could emerge from conventional materials when innovative engineering challenged established assumptions and pursued creative solutions to demanding requirements. The Mosquito remained untouchable because one engineer refused to accept that impossible meant impossible, and instead proved that wooden wings could outfly anything the enemy could build.